class. Welcome to another video for this course. In this video, we are going to study section 3.3, global optimization. So far, we learned about extreme values, and we learned that we have two types of extreme values, global or absolute, and also local ones. So we learned that when you have a function, so suppose you have a function of f of x, then this function may have, in general, for a function, we can define the global, or also it's called absolute extreme values, like absolute maximum or absolute minimum, and also local, and it's called relative or local extreme values. What is the difference between being absolute and local? It goes back to the definition. So if it's absolute, it means that for the function, you look at the range, so you look at all the output values, and you pick the extreme value, which means that you pick if it exists, you pick the greatest value, the largest, the bigger value, and you pick the smallest value. So it's over the entire range, entire output. So it's like, look at the set of all output values and then pick the smallest value and largest value. So this is gonna be absolute minimum, absolute mean, and this is gonna be absolute max. Okay, so that's about this. And for local ones doesn't look at the entire range. No. So what happens is that it's locally, like, okay, your function may have an x. Suppose this is the graph of function, right? So what happens is that at some neighborhood locally, for example, over this range, over this part of the domain, then there is one local maximum, which means that the height of this input value or this output value, okay, is greater than anyone in its close neighborhood, right? Or for example, this one is a local minimum. It's not the absolute minimum, but it's local. Why? Because for the people, for the values around of it, it has the smallest minimum. So this is a local minimum, and this is local max, and this is a local min. Okay, so that's the difference between being absolute extreme value and local extreme value. When you say absolute, it's over the entire range. But when you say local, so it's like we are looking at the function over pieces, and then, okay, in this piece, this is, if you just cut your function and look at that piece, then you have a maximum. If you look at this part of the function, it's minimum. Okay, now in this section, we want to closely look at the difference between absolute and local extreme values, and also focus on absolute ones, because I think in last section we focused on determining local ones, but we hadn't done a concrete study and analysis for the global or absolute extreme values. So let's do that. So for example, in this picture, you see the graph of function f, and you see that this graph, okay, for input value c, the output, it has the highest height. You see that? So that's the greatest output value. So that's going to be global maximum, absolute maximum. But then for point A and B, look at A and B. Okay, so the height for A is not the greatest. The height for B is not the smallest. However, in their close neighborhood, if you just focus on the values around them, then at A, it has a relative maximum, local max, and then at B it is a relative minimum. So in this picture, we want you to like see the difference being global and relative, being absolute and local. So if it is absolute or global, it means that it's over the everything. You come, that value is greater than anything. But for local, it's just locally extreme value. So I think now you should see the difference between global and relative. And by the way, you may argue that, okay, so at C, we can also say that that's local. That is true, because even, I mean, not only it's greater than anything, it also, in its neighborhood, it's also. So at C, f of C is local max and global max. But the other two, f of A and f of B, they are just local extreme value. Okay, so now we know how to determine the local ones. We learned the second derivative test and first derivative test, and we saw examples of how to use them in order to determine the local one. Now let's talk about global one. How can we determine global extreme, absolute extreme values? So we have a theorem, extreme value theorem, which is going to be very fundamental when we are talking about extreme x value, which says that if you have a continuous function on a closed interval, so it doesn't have to be even, I mean, this theorem works for any closed interval. So it's not just the function over its domain. It doesn't have to be, it could be on domain, but the point is that if you have a function f, which is continuous on closed interval. So let's say something, so I'm not saying that it has to be like this, but something like this. So a graph like, suppose this is A, this is B, and this is f of A, and this is f of B, and your graph might look like something like this. I mean, it can be any graph, but because it says continuous, so it should be a curve. So I'll just draw a random curve that is continuous, okay? So f is continuous on the closed interval, and then f attains both absolute minimum and absolute maximum. That's the theorem. So if f is continuous, the theorem says that if f is continuous on a closed interval, then f attains, or it has absolute max, absolute maximum, and absolute minimum, which means that there is a point that is great. So in this picture, this is absolute, this is exactly the absolute max because it has the highest degree. So this is going to be the absolute, f of B is going to be the absolute maximum. That's the maximum height. And f of A is going to be the absolute minimum because that's the smallest, height. Okay, that's what this theorem says. It says that the condition, the necessary condition is that f should be continuous on a closed interval. So this is not about open interval. So there are two crucial conditions: being continuous and having a closed interval. Then f has both absolute max and absolute mean value. And the rest is just notation that says that there is a point. So for example, so in this case, I mean, in this picture, in this random example, the absolute mean and max, if attain those absolute, those maximum and minimum height at its endpoint, right? So in that example is the case that f attains, it's not here, I guess. Okay. Yeah, so I'm gonna explain it in detail. So this is the case that if reaches the maximum height and minimum height at the end points, but in general there is a point. So it says that there is a value between A and B, such that it is a maximum or minimum. I'm gonna give you more examples, graphical example. For example, suppose your function is like this. So this is f of A, and then this is f of B. So the question says that there is a point in between A and B that is absolute max and absolute minimum. And in this case, you see this is absolute minimum. This has the smallest height. So that's the x. So here, whatever is this height, that's going to be the absolute minimum. It's none of the, so this is the case that the absolute minimum is none of the endpoint. It's neither A or nor B. And there is the absolute maximum is right here. It's f of A. So the absolute maximum is at the endpoint A, but the absolute minimum is somewhere in between. Let me give you another example. Something that it doesn't happen. I want to give you an example that it's neither at A nor at B. So something like, so let's say this is f of A, right? Something like this, for example. Maybe go higher. Okay. And this is gonna be f of A. So f of B. So look, in this example, the absolute max and absolute mean is neither at A nor at B. It's somewhere in between. So this is the highest, the greatest height. So here at this x value, whatever is this x value, the function reaches the maximum height. So here we have the maximum height, which is absolute maximum, because this height is greater than any other height over this range. And here, right at this value, whatever is this value, let's call it x of max, and this is x of mean. So this height, whatever is the height here, that's gonna be the absolute minimum, So this is an example minimum. So this is an example of the case that the absolute max and absolute mean is neither at A nor at B. So it's not at endpoints, it's somewhere in between, you see? So what does this theorem tells us is that if you have a continuous function, look at all of these examples, all of these drawing. If you have a continuous function, so the first condition is that the function has to be continuous. Over a closed interval, function definitely has absolute max and absolute mean. It could be at the endpoint, but it also could be somewhere in between. So, okay, so here is the thing. This theorem tells us about existence. So the theorem tells us that, okay, if you have a continuous function and you are looking at over a closed interval, so definitely the extreme value, the absolute extreme value exists, but it doesn't tell you where it is or how to find it. So we need to have a strategy or approach on how to calculate it. Okay, so this note is very, very important. Please highlight this in your reading. So far, we need an approach to finding the absolute maximum and minimum of a continuous function on the closed form. And we have to do all of these steps. And I'm gonna explain these steps one by